Welcome back to the third video for Tech 240 for August 26th, 2020. In this video, we're going to solve the second example problem that deals with KVL and KCL. So I'm going to switch over to the document camera. All right, here is the circuit that we left off with in the last video. And we are given some of these things. We're given what the value of the current through resistor 3 is, and we're given where the ground is, and we're given what the value of the voltage source on the right is, V sub R, and we're given the resistance values of all the resistors. That's it. And we want to find the value of all the current flows, all the voltage drops, and the voltage sources, and the voltage at each of these nodes, A, B, and C, and D. All right, so remember we had that little three-step procedure that I outlined in the first video. So the first thing here is to look at this circuit and say, is there a way of solving this through the method of combining resistances and finding R total? And you might stare at this for a little bit and think about it. Is there a way of combining these? And I can't even begin to see a way of combining these. I can't even see two resistors that are in parallel with each other, or two resistors that are in series with each other. So the answer is clearly no. I can't even find a pair of resistors that are in parallel or series. So I'm not going to be able to combine those and solve them through the method of total resistance or combining resistors. So I'm going to have to go to using KVL or KCL. And so with KVL and KCL, the first thing is to make sure everything is labeled, including the values of the resistors, the names of the resistors, the voltage sources, the nodes, all of that. And oftentimes that'll all be done, but what's not usually done is to assume a direction of current flow. Once again, this is just a guess. It really doesn't matter. It won't affect the final result, but it will affect the way your equations look. All right. So let me go ahead and assume some current directions. If you do this on your own, then your assumed current directions might be different than mine, but that is totally fine. So I'm going to assume that I1 goes from left to right, and I'm going to assume that I2 goes from right to left, and I'm going to assume that I4 goes from right to left also. Again, that's just arbitrary. That's just what I decided I wanted to do. And let me clarify something that I said about 30 seconds ago. I said it won't affect your final answer. All right, that's true, but you have to look at the arrow. All right, so if your arrow is going right to left, then you're going to get the same thing as I do. But if your arrow is going left to right and mine's going right to left, then our two answers are going to be the negative of each other. All right, so if I write my arrow like this and I get, I don't know, I get negative 2 amps, then if you write your arrow left to right, then you should get the opposite of that, which is 2 amps. Okay, so when I grade these, when I'm looking at your lab 3 and I'm checking your answers, I have to see your arrows here. If you don't have arrows written in here, I don't know if your answer is right or not. Because if my arrow is one way and I get negative 2 amps and your arrow is the other way and you get negative 2 amps, that's different. You know, that's different. That says something different. Whereas if my arrow was going right to left and I get negative 2 amps, and your arrow is going left to right and you get 2 amps, that's the same thing. All right? So I guess when I say it won't affect your answer, I guess I need to be more specific about that. It doesn't affect the final result, because we know that if we get a negative value for current or voltage, then we know that we just happen to write the arrow in the wrong direction. But as long as we know that and recognize that, it's no big deal. But when I'm checking your answers on the lab 3, or in or in the exams or quizzes, then I have to be able to see your arrows on here. You have to write your arrows in here, because otherwise I can't tell if your equation is correct or not. All right, so it's pretty common. I see students that just dive into the problem and start writing equations, but you're going to get really confused, and I'm going to get really confused when I try to help you or figure out what happened in your problem if you don't have your arrows in here. So you have to have your assumed current flows drawn in here. So draw in your arrows. Okay, all right, that's enough about that. So I've got my assumed current directions drawn in here. Everything else I think is labeled. So now I'm going to see, first of all, is there anything I can fill in without even doing too much work? And there is. First of all, this tells me that this is ground, and D is right here, and there's nothing to drop voltage between D and this ground symbol. So voltage D is at ground, which is 0 volts. So I can write in 0 volts for D, voltage at D. And we're given a few things. We're given the voltage of the right voltage source. It's 20 volts, so let's write that in. And we're also given the value of I3, so let's write that in. That's 3 amps. And that's it that's given, but there's at least one thing that I can see that I can easily solve, and that is the voltage drop for resistor 3, because I know R3 and I3, so I can use Ohm's law, and I can find V3. So I'm going to do that first. That's easy. V3 equals I3 R3, and I3 was 3 amps, and R3 is 4 ohms. 3 times 4 is 12, and amps times ohms gives me volts. So my voltage drop across resistor 3 is 12 volts. Okay, so I'm going to write that in. 12 volts. Good. All right, so I got a good start. All right, so now what do I know? Keep track of what you know and what you don't know. I know everything about this resistor right here, so this is a known, and I know about the voltage here. So I know everything I am going to need to know about this voltage source right here. So this is all known and this is known. But I don't know this, or this, or this, or this. So I'm going to try to make loops or find nodes where there is exactly one unknown voltage drop or current, respectively. If I'm making a loop, I got to find one unknown voltage drop. If I'm looking at a node, I need to find a node with one unknown current flow into or out of that node. Okay? You might have to use either one. Don't get stuck on one and ignore the other. Okay? Look for loops and nodes. It's really common. Another really common mistake that I see students make is they get stuck on looking for loops, and they totally forget that, oh, I can also look for nodes where I have exactly one unknown current flow. All right, so if you get stuck on one, look for the other. All right, so the first thing I'm going to do is I'm going to think about what I know and what I don't know. And the first thing that pops into my mind is, all right, I know this and I know this, so a really easy loop to make is this right here. And I could go clockwise or counterclockwise. Normally, I'd prefer to go with the direction of most of the arrows, so that just makes the equation look easier. So I'm going to write a KVL equation for the lower right loop. I'd really prefer that you write this out like this. That helps you keep your thoughts organized, and it helps me to kind of see what you're doing. Oftentimes, students come to me needing help on some of this, and I look at their page and I have no idea what they've done. It looks like just a scramble of equations and numbers. So help me help you, okay? So that little Jerry Maguire quote there. All right, lower right loop, and I want to go counterclockwise because I think that'll make it look a little nicer. All right. So it doesn't matter where I start, it makes no difference. So I think I'll start at node A, and I'm going to go counterclockwise around this way. So the first thing I get to is resistor 2, and I'm interested in voltage drops. Okay, VL is all about voltage drops. And we're going with the direction of assumed current flow, so it's a positive voltage drop. So I have V2. If we were going against the flow of assumed current, if I had assumed my current was going this way, left to right, then I would write negative V2. And that would be fine. It would work out, but I assumed it was going this way. So that's why I have positive V2 and not negative V2. So I have V2, and then I come around to resistor 3, and once again, I'm going with the direction of assumed current flow, so it's going to be a positive voltage drop. So I write plus V3. Once again, if my arrow here was going the other direction, then I would have a negative voltage drop. I'd write minus V3 as I'm going this way around the loop. All right, so I've got V2 plus V3, and then I continue on my circuit, and I get to the negative sign first of the voltage source. So I take the first sign that I come to, so it's going to be minus V sub R. And then I keep on going, and I get back to where I started, so I set it equal to 0. All right, so the whole reason why we wrote this equation is because there was only one unknown. V2 is unknown, but I know V3 and I know VR. So I can plug those numbers in, and I can solve for V2. So V2 plus V3 is 12 volts, minus VR is 20 volts, equals 0. All right, so rearranging here, don't skip too many steps because you will make a mistake in the algebra. I've seen it enough to know. All right, so I'm going to move 20 volts over to both sides, add 20 volts to both sides, and I'm going to subtract 12 volts from both sides. So when I add 20 volts to both sides, I get 20 volts on the right side, and 20 volts cancels out on the left side. And I subtract 12 volts from both sides. That cancels out the 12 volts on the left side, and we subtract it from the right side. And 20 volts minus 12 volts gives me 8 volts. So V2 equals 8 volts. I'm going to write that in. And now, as soon as I know V2, I can use the fact that I know R2, and I can solve for I2. I2 equals V2 divided by R2. V2 was 8 volts, R2 was 2 ohms. 8 divided by 2 is 4, and volts divided by ohms gives me amps. Don't forget to write in your units here. If you don't write in your units, then you're only going to get partial credit because the units are critical. So I2 is 4 amps. Great. All right, maybe I'll write that in just to tell me that I know this. Okay, so I've gone as far as I can go with that equation in that component. All right, so now I know everything there is to know about this and this and this. And I still don't know this or this or this. All right, so I'm looking for loops or nodes where I have one unknown, right? All right, so most people's inclination is to look for loops first, which is fine, just so long as you don't get stuck on loops. So let's try to find a loop with one unknown. Okay, so we need to find a loop where we only have this or this as an unknown. So I'm looking at this loop. Nope, that doesn't work because I have 2 unknowns. I'm looking at this loop. Nope, that doesn't work because I have 2 unknowns. I'm looking at, what else can I look at? I can look at this loop, the whole lower one. That doesn't work because I have 2 unknowns. How about, oh, there's this one. There's the upper loop. I can look at this loop, but that doesn't work because there's 2 unknowns. One equation with 2 unknowns does me no good. It doesn't help. So I'm kind of stuck. I don't see any loops with only one unknown, right? So I see a lot of students get stuck right about here in this type of problem because they don't see any loops that have one unknown. So what do you do? All right, so it's true. I don't see any loops that have only one unknown. So don't get stuck on KVL. If you don't see any loops, then look for nodes that have only one unknown. All right, so let's look for some nodes. All right, let's look at that node. Do you know what current is coming through here? No. Do you know what this current is? No. So we know we have more than one unknown. And we also don't know this current here. How about node B? Do you know this current coming into it? Yes. Do we know this current going through here? No. Do we know this current through here? No. So that has more than one unknown. How about node A? Do I know this current? No. Do I know this current? Yes. Do I know this current? No. So that's two unknowns. So that doesn't work. But now look at node B. So I've got 3 wires connected to node B. Do I know this current coming in? Yes. Do I know this current coming out? Yes. Do I know this current? No. But that's the last one, and that's the only one I don't know. So it looks like I can do a KCL equation at node B because I have 3 wires coming in, 2 of them I know, and it's only one that I don't know. All right, so that should work. I can do a KCL at node B. KCL at B. All right, so KCL says all of the currents in equals all of the currents out. That just means sum of the currents in equals sum of the currents out. So what are the currents coming in, or what are the currents we assume are coming into node B? There's 2 of them. We assume that I3 is coming in, and we assume, actually we now know, that I2 is coming into node B. So we have 2 coming in, I1 plus I2, and we set that equal to whatever is coming out. What's coming out? There's only one coming out, and it's I3. All right, this is going to work because I know everything except one of these. I don't know I1, but I know I2 and I know I3. So what were they? So I1 plus I2 was 4 amps equals I3, which was 3 amps. So I need to subtract 4 amps from both sides. 3 amps minus 4 amps gives me negative 1 amp. Oh, okay, well, I got a negative current value, but like I said before, that's no problem. Don't go back and change anything. That will just mess you up, and it will mess me up as I'm trying to understand what you did in the problem. So just go ahead and write it in. I1 equals negative 1 amp. Write it in just like that, and as long as I can see your work and it all makes sense, then this is fine. It's fine to have a negative current flow. Just so long as you understand what that means, and that is that actually we've got 1 amp flowing from right to left through resistor 1. All right, negative 1 amp flowing left to right is the same as positive 1 amp flowing from right to left. All right, no big deal. But now we can use this result and solve for V1, because V1 equals I1 times R1. I1 is negative 1 amp. R1 is 3 ohms. So V1 equals negative 1 times 3 gives me negative 3 amps times ohms gives me volts. All right, so write that in. V1 equals negative 3 volts. All right, so what that means is that we thought we had a voltage drop from this side to this side. That's what the arrow would indicate. Arrow from left to right indicates a voltage drop from left to right. But actually, because we got a negative voltage drop, what that's telling us is that actually we have a voltage drop from right to left. All right, so actually, in this circuit, we drop 3 volts from this side to this side. Okay, that's kind of important to know. All right, so I'm going to write this in just so I know that it's known. I1 is -1 amp. All right, so now I know everything there is to know about this one, and this one, and this one, and this one, and I only have two unknowns left, this one and this one. So find a loop or a node that will work for us, where we have one unknown. So it doesn't matter which one. I can see two, at least two. Honestly, I can see more, even more ways to go about this problem. But I think the next one I'm going to do is this lower left loop. And I think I'm going to, well, you know what? Normally I would do this by going clockwise like this. But let's mix it up just to kind of mix up the examples here. And I'm going to do this loop, the lower left loop, because I have only one unknown, and I'll be able to find V sub L. So I'm going to do a KVL loop, and it's going to be the lower left loop. And I would normally go clockwise because that's the direction these arrows are pointing. So it might make the equation a little bit prettier if you go clockwise. But I'm going to mix things up, and I'm going to show you that you can go either way. So I'm going to go counterclockwise, just to give a different example. So for my example, once again, doesn't matter where you start. So I'm going to start here at C. I'm going counterclockwise. So the first thing I come across is the positive sign of V sub L. I'm going to have positive V sub L, which is just V sub L. And then I keep going, and I come up to resistor 3, and I'm going to go against the direction of current flow, or assumed current flow. In this case, it was given, but it doesn't matter. I'm going against the direction of current flow, so I have to say minus, and we're dealing with voltage drops, so this is V3. Okay, and then I keep going, and I get to resistor 1. And once again, I'm going against the direction of assumed or given current flow, so I have to say minus. And we're dealing with voltage drops, so this is V1. And then I get back to my starting position, so I set it equal to 0. All right, so be a little bit careful here. We might have some negative of negatives, double negatives, so be careful keeping track of your negative signs. So I can plug in what I know. VL I don't know, so just leave it like that. VL minus, what is V3? V3 is 12 volts. Minus, what is V1? V1 is negative 3 volts, so this is what I mean. Be careful here. I'm going to write it like this. I know I have to minus it, because that's what my equation right here said, because I was going against the direction of current flow. But I have a negative voltage drop, so I have this when I plug in for V1, okay? So this is what my equation looks like when I substitute in values. So a negative of a negative is actually a positive, right? So what I'm going to do, well, you know what? I might just rewrite it just to make it clear. All right. When I subtract a negative 3 volts, I'm actually adding 3 volts. All right. I didn't want to skip that step just to make it as clear as I possibly can. So now I'm going to add 12 volts to both sides to get rid of that, and I'm going to subtract 3 volts from both sides to get rid of that. And 12 volts minus 3 volts gives me 9 volts. Okay, so I can plug that in. V sub L gives me 9 volts. All right, so I can write that in if I want to. And now the only unknown component is this one up here. So I can choose this big outer loop, or I can choose the upper loop, or I can choose kind of any weird combination will work. I usually try to choose the simplest loop that I can. So normally I would probably choose this outer loop, because that's probably the simplest loop. Your equation, if you're going this way, would be, if you start here, you would come to resistor 4, so you'd say V4 and you come to the positive sign, so you'd say plus VL, which is 9 volts. Then you'd come over to here, and you come to the minus sign, so you'd say minus VR, which is 20 volts, equals 0. So that would honestly be probably the easiest way, but just because I want to give as many examples as I can, let's do it slightly differently, and I'm going to choose this loop right here. All right, so I think I will choose to go counterclockwise, and I'll start at A. Okay, so KVL for the upper loop, and I'm going to go counterclockwise. And I'm going to start at A. So when I start at A and I go counterclockwise, the first thing I come to is resistor 4, and I go with the arrow, so it's a positive. So it's just V4. And then I continue on, and I'm going with the arrow through resistor 1. I'm going with the arrow, so it's a positive. Don't worry about that negative current value. We'll get to that. But right now, we're just going with the arrow. So it's plus V1, okay, because we're going with the arrow. And then I come to this one, and I'm going against the arrow, so it has to be a negative, and it's resistor 2. The voltage drop, so it's V2, and then I come back to my starting point, so I set it equal to 0. Okay, so the only one I don't know is V4, so I can plug in my unknowns. V1 was negative 3 volts, so just plug that in like it is. So we have plus negative 3 volts minus whatever V2 is. V2 is 8 volts. Equals 0. So V4, in this case, I think I might combine these first, and then I'll move it to the other side. So negative 3 volts minus 8 volts gives me negative 11 volts equals 0. Now I move 11 volts to the other side by adding 11 volts to both sides, so V4 gives me 11 volts. V4 is 11 volts. All right, so that's all my components. I've got everything. I've got all my components, and the only thing left are these nodes, figuring out what is the voltage measured at these nodes. So it doesn't matter which one we do first. Let's do A first. So I'm measuring the voltage at A, so my red probe goes on A and my black probe goes on ground, because we're always measuring relative to ground in these things. So what we do is we just take the easiest route to get from ground up to here. And when I do that, I go from ground up to A. The easiest route is to go this way. And you're going to do that. You're going to gain VR, which is 20 volts. So from here to here, you gain 20 volts. So right here and anywhere in this area, all of which is really node A, you're at 20 volts. All right, so we could write that out. The voltage, I'll write it over here. The voltage at A equals ground, which is at 0 volts. And then when we go from the negative to the positive, we're going to gain 20 volts. So the voltage at A is 20 volts. All right, so we're not really, when we're finding the voltage at these nodes, we're not really using loops. We're not using KVL or KCL when we're finding the voltage at these nodes. We're just looking at what was the voltage drop that we found across these components and these sources. All right. So the voltage at A is 20 volts. All right, what's the voltage at B? All right, so I'm measuring like this from ground to the voltage at node B. All right, so we want to go from ground up to B. The easiest way is probably to go through this resistance, all right? And we know what the voltage drop of resistor 3 was. V3 was 12 volts. So what that tells us is that as we're going with the direction of the arrow, from here to here, we dropped 12 volts. Okay, so from here to here, we dropped 12 volts. And here, which is at the same voltage as D, and all of this down here, we already know we're at 0 volts. So we're at 0 volts here, and we had to drop 12 from here to here. So that means the voltage here must be 12 volts, right? It has to be, so that we can drop 12 volts from here to here and be at 0 down here, like we know we are. Okay, so the voltage at B must be 12 volts. Voltage at B must be 12 volts. And the last one is the voltage at node C. So we're measuring from node C to ground. So the easiest way is to start from ground and then to go this way. And from here to here, we're going to gain V sub L, which was 9 volts. So all along here, we're still at 0 volts all along here. But as soon as we go from here to here, we gained 9 volts. And we know these are just wires, so they have no voltage drop. So this is all at the same voltage drop. So we're at 9 volts here, which means that we also are at 9 volts here at node C. So the voltage at node C must equal 9 volts. All right, so that completes the second example. And if you can do that by yourself, if you were able to do most of that even by yourself, then you are definitely ready to take a crack at lab 3. All right, so that was a couple of examples using KVL and KCL. And don't forget, you can use Ohm's law, you can use voltage divider, and all the tools in your toolbox to solve the circuits in lab 3 and any future labs as well. All right. A quick note. So this is actually the most advanced circuit analysis tool there is. There isn't anything that gets more complex than this in terms of circuit analysis. So when computers are doing circuit simulation like Tinkercad, what it's doing, as well as what multi-sim and all those circuit calculation simulation tools, they're actually doing calculations like this, KVL and KCL. For our purposes, I'm actually going to keep it a little bit simple. I will make sure that whatever equations you're going to write, you can always write an equation that has one unknown. All right, so I will guarantee you that right now. If I'm giving you a circuit to solve, it can be solved finding the answers by solving KVL and KCL problems where you have one unknown in one equation. All right, it's always going to be possible to do that. In the real world, you can certainly come up with circuits where it's not possible to find a KVL or a KCL equation that has only one unknown in it. And so in that case, what has to be done is solving equations simultaneously. You may have done that in some math class previously, where you can come up with a certain number of equations, and as long as you have the same number of equations as you have variables, it can be solved. You know, for example, you might be able to come up with 2 equations, x plus y equals 5, and x minus y equals 1. All right, so if you can solve both of those simultaneously, there are a variety of methods to do that involves more mathematics than it does circuits, understanding of circuits. So that's now a math problem. And there are different ways to solve that, and computers can solve those simultaneous equations. So as long as you have the same number of equations as you have variables, unknown variables, you can solve that, and the computer can solve that. But that's just a step beyond what we're going to do in this class. So it does actually get a little bit more complicated, but we're not going to go there. I just want you to know kind of how it's done, how circuit simulation tools are doing that, but we're not going to solve systems of simultaneous equations. All right. A couple of recommendations as you're doing lab 3. First of all, make sure you always show units. Your volts and amps and ohms. If you don't show your units, then you're only going to get partial credit for your answers. That's the way it is. So make sure that you double check and show units in all of your answers. Another recommendation that I have is to work slowly, actually. If you try to rush through here, if you try to rush through Lab 3, I just about guarantee that you're going to make a silly mistake somewhere. I mean, I would too. I would make a silly mistake if I tried to rush through it. And that will come back to bite you because it will throw everything else off. And then you'll get 3 steps down the road and you'll say, what is going on here? I don't know what's going on, but something is messed up. And you're probably right. It was messed up 3 steps ago because you made a silly mistake because you were rushing through things. So slow is fast. You may have heard that before. If not, I'm telling to you, slow is fast. Working slowly through it is going to be most of the time the fastest way to get through the lab. All right, so work through it carefully and slowly, just like I did with the example problems that I just showed you. All right. So that's going to wrap up today's videos. I know this was a little bit long. This is one of the more conceptually challenging concepts in the first third of the semester. I promise you upcoming videos will not be as lengthy as these. Okay, so good luck. Let me know if you have any questions on Lab 3. And if not, then have a great weekend, and I'll see you next time.